Welcome back. Today we're going to talk about the way that we get our electricity and the challenges that presents for the way we are going to need to get our electricity in the future, which is without the use of fossil fuel combustion. I want you to take a minute and think about the amazing reality that when you turn on a light switch, there's automatically, or it feels automatically, electricity there to turn on that light. But nobody on the generation side knows exactly when you're going to turn on the light or how many lights you're going to turn on. The fact that that works is the result of what has been called the most complex machine ever built, the electricity grid. And today we're going to talk about the way that the United States electricity grid functions and the way it's been built over the past century and more to provide consistent, reliable power that is always there, no matter how many lights you need to turn on, with very few exceptions. I put this slide up at the end of the last video to give you a roadmap of where we're going. We're going to start in today's video with the electricity grid and the architecture that provides that power. And then, as I mentioned last time, Dr. Raja Gopal will go forward with segments on renewable electricity and the challenges they pose that poses to the 21st century grid, and some solutions such as grid storage, flexibility of demand, and electric vehicles. But today we're going to dive in on electric grid architecture, so fasten your seatbelts and let's get going. This diagram shows the general way in which electricity is delivered from a generator, which you'll see on the left-hand side of the screen, to a consumer, like your house. I've broken it into pieces, but I want to talk through the whole diagram at the beginning, and then we'll dive in to the details of each segment in a minute. So let's start on the left. You have a power plant. A power plant could be a nuclear power plant, could be a coal-fired power plant, could be a natural gas-fired power plant, could be a hydroelectric dam. I'm going to leave wind and solar off of this diagram for a minute because those are those are newcomers to the electricity grid. So that generator generates electricity, sells that electricity into a wholesale market, and sends that electricity out into a transmission network. And in between that generator and the wholesale market and the so-called grid system operator that manages that, and that's on the left-hand side of the screen, there's a utility, your local utility. So here in Rhode Island, that's Rhode Island Energy. And that utility manages the distribution of that energy from the big transmission lines that are coming from the generator down through to your house. The biggest point I want you to take away from this slide, and the thing that's missing from this diagram, even though it doesn't appear to be missing, is that there is no storage in the system. The amount of electricity that the generator makes has to exactly match the amount of demand that all of the consumers are asking for at any given instant. So if you think about that, right, you have a coal-fired power plant or a natural gas-fired power plant where coal is being burned and that's producing steam and that's spinning a turbine, which is generating electricity. That production needs to exactly match consumption. And how we do that is through a whole series of complicated networks and markets that are built to ensure both reliability, so that when you turn on the light switch, electricity is there, and also ensure affordability, or as much as possible. So the 20th century grid has been built with those ideas in mind. And it's really quite amazing, if you think about it, that we can do that in a way where production matches consumption without any buffer of storage. There's one more thing I want you to keep in mind about the 20th century grid, or the grid the way it works now, that's really important and may very well change in the coming decades. And that is that right now, power flows in one direction. It flows from the generator to the consumer. And the reason I say that may change in the future is that as consumers, for example, put solar panels on their roofs, you have the potential for power flowing in more than one direction. And that's going to be a challenge that the grid is going to have to we're going to have to deal with from an engineering perspective. And Dr. Raja Gopal will talk about that in a future video. But just keep in mind that the system is built right now for a one-way power flow. So I'm just going to walk you through, for those of you who are a little more physics-oriented, the way that this works. If you're not physics-oriented, don't worry about it too much. I'll go over some of the terminology in just a minute. So on the left-hand side, you're seeing here a generation station, again, a power plant. That power plant is connected to a transmission network, and there's a transformer or a series of transformers that change the voltage of the electricity to a very, very high voltage. And so you've probably heard of the word high voltage wires. We use very high voltages for transmission of electricity across long distances because that reduces the amount of resistance and the amount of line losses, the amount of energy that's wasted in transmission. And then on the back end, sort of outside your house, if you look outside your house on any electric pole on your street, there's usually a white cylindrical unit on the top of that pole. That's a transformer that changes the voltage back down to the 120 volts that you run on in your house, or if you're in Europe, it's 220 volts, but it's relatively low voltage. And the reason for that is just that it's much safer. High voltages are really dangerous, easier to have accidents. And so at the homeowner side, we transform that electricity back down to a lower voltage, and then that's consumed either by a big factory or even down to a house. Just to give you a little bit of the terminology that you'll hear throughout this series of videos, just so you're up to speed. So you'll hear a lot about power, the word power. That has a specific meaning in physics, which is energy per unit time. So the amount of energy you deliver over a second is power. You'll hear that in watts. That's the unit of power, and so you'll hear watts or kilowatts or megawatts. Those are all units of power. In electricity speak, power is voltage times current. And there's an easy analogy for you to think about voltage and current. Voltage can be thought of as the height of the waterfall. So imagine a river and it's flowing over a waterfall, and the higher it is, the more energy the water will have when it hits the bottom. And that can be thought of as voltage. So it's a difference in electric potential, and basically the higher the voltage, the more power can be delivered. Current can be thought of as the amount of water in the waterfall. So a little teeny stream that falls a long way doesn't deliver as much power as a giant river that falls that same distance. So if you want the same amount of power, you can have a very big waterfall with not too much water in it, or you can have a very small waterfall but with a lot of water in it. The second thing I want you to wrap your head around when you're thinking about electricity, and I'll show you in an illustration in just a minute, is that every time you take a little bit of energy out of the system, like you turn on your microwave or you turn on your toaster, that will reduce the total amount of power available to the person downstream from you. And you even recognize this in your house. Sometimes you'll flip on the vacuum cleaner and the lights will flicker or dim just for an instant. And what's happening there is the voltage in your house is dropping just a little bit as you have a new demand. And then almost magically, it ramps back up, but it's not magic. It's actually engineering, and it's engineering of the electricity grid. And the reason I say almost magically is, remember, there is no storage in the system. And so what's happening is there's a dip in voltage, and the system is sensing that, and we'll talk about how, and then increasing the total amount of power flowing in the network to make up for the fact that you just turned on your vacuum cleaner. Now, of course, a vacuum cleaner is a trivial amount of power, but this has to be done at the city level or at the state level, right? We need to anticipate and respond to changes in demand and build a system that is robust to that. So just to illustrate this, I have here on the left, electricity is coming from the power plant, and it's at very high voltage. It comes into a substation. That substation sends electricity out to a network that's going to your house. And let's say you have a series of houses along a transmission line. So the first house is receiving power. It's at 120 volts, the voltage we use here in the United States. And that house uses some power. And that means that there's a little bit less power available to the next house down the line. Here I've made it 118 volts. That would be a big drop, but just for purposes of illustration. And then if that house uses a bunch of power, then the next house down the line has a little bit less available to it. But as anyone who has tried to plug their hairdryer into a European socket will know, Our appliances are built to tolerate a certain voltage. And so there has to be very strict regulation of how much the voltage is at every house in order to ensure that you don't burn your appliances up. And so that's part of the engineering of the system. A couple more concepts I want you to keep in mind. And this has to do with some of the things that Dr. Rajagopal will talk about in future videos. So the first is that electricity flows through this super complicated transmission network according to the laws of physics. And what I mean by that is that the total resistance in the electricity lines that are moving current from one place to another will determine how much flows through one line versus another. I'm not going to go into a lot more detail, but suffice it to say that unlike a road network, where if you have one road that's empty and another road that has a traffic jam, people can just choose to go around, the laws of physics constrain how much power can flow through each wire in the network, such that one part of the network can be congested and not be able to transmit any more power, while another part of the network is still relatively empty, and we can't just shift the current to another wire. And the reason this causes a problem is that when we are building in new power sources into the grid, we not only have to think about how much power those are producing, but how they connect into the existing network and how easy it is to get electricity from that new power source down to someone downstream. In general, the voltage in the network is a function of how much supply, what transmission lines that supply is going through, and how crowded they are with power, and how much demand there is. And then finally, we need a way to monitor the voltage in the network more frequently than every second in order to keep the system operating. We can't allow voltages to drop. So these are some of the major challenges. And especially these are challenges because there's no storage in the system. So that was a lot of physics and engineering. Let's talk a little bit about how the market system works in our electricity market. And I'm going to return to this basic diagram, and I'm going to start on the left with what we call the grid system operator. So I'm showing you here a map of the different independent system operators in the United States and Canada. And each one of these different colors represents a region. So I'm giving this lecture in Rhode Island. The lights in this studio are provided by the New England ISO Consortium, an independent system operator, and they're in charge of the starting part of the electricity grid. So what do I mean by that? They run a power market that is set up to ensure that supply and demand are met and to ensure economic fairness. They provide wholesale prices for different services. So you may not know this, but the price that a giant consumer of electricity pays for electricity is different from what you pay at your house. There are wholesale and retail prices. There's actually prices in between. And they also manage the connection of electricity from one region to the next. So for example, here in New England ISO manages power that comes down from Canada and power that comes across from New York. And their job is to ensure that supply matches demand. So what do I mean about supply and demand, and how would you even go about matching that? What I'm showing you here in this graph is a typical load on a summer day. And I'm just going to use the word load as synonymous with demand. So your vacuum cleaner is a load. It's demanding electricity. Or your lights are a load. They're demanding electricity. So this is the load or the demand on a typical summer day. And you can see that at midnight, it's pretty low. All the lights are off. You're probably not vacuuming. When you wake up in the morning, you start demanding more and more electricity. That demand stays high during the day, not because of what you're doing in your house, but probably what you're doing in your office or because industry is ramping up, and then it ramps back down at midnight. So the x-axis on this graph is time, and the y-axis is how much electricity is being demanded. Now, this isn't just for your house. This is, say, for a city, city of Providence, for example, where I live. So that's the typical demand. How would you build out a system that matches that demand instantaneously? So the first part of the system that we talk about, the first part of the load, is called base load. And that's the amount of electricity that's needed all the time. Day or night, summer or winter, year to year, a city is going to need a certain amount of electricity. And so in the planning stages for electricity generation, you can say, okay, well, if we're going to have a city of this size, we're going to need at least this much power all the time. So we need this many power plants available to provide that power. And that power can be really slow and steady. It doesn't need to ramp up and down with demand. It's just always going to be there. And so it can just run pretty close to full steam all the time. And then we also need to anticipate that there's differences over the course of the day or maybe over the course of a season. So we have an intermediate load that's needed sometimes. So we need these power plants to exist, but we also need to understand that they're not going to be running all the time, and they're going to need the capacity to ramp up and down. So base load, which is always needed and can be counted on to run 24/7, that's typically provided in this country either by nuclear or by fossil combustion, either coal or natural gas. But neither nuclear nor coal can ramp up and down really fast. And so more and more, the intermediate load, the sort of daily fluctuations, are provided by gas-fired power plants, or now more and more by renewables that can come online, for example, during the day, like solar panels. And then some days, but not all, we have an extra spike in electricity demand. So for example, if you're in the Texas grid and you have a particularly hot summer day, the air conditioning demand is going to be even higher than usual, right? And so we're going to need power plants to supply that demand because there's no storage in the system. And those are just needed occasionally. As a result, those are power plants that can ramp up really fast. They're typically provided by natural gas, sometimes a little bit by oil, and they are the most polluting sources. So you may hear people who talk about energy efficiency talk about shaving the peak. What they're meaning is, how can we reduce demand at those really peak times when electricity production is sort of its most dirty or its most polluting? So this concept of base load and intermediate load and peak load are dealt with in different ways by the market. Base load can be thought of years in advance. You know you're going to have a city, you know you're going to have a certain amount of demand, you know you're going to need a certain amount of power plants to provide that demand. You can usually predict the daily fluctuations for a region pretty easily, right? Even if I decide to turn on my light and you don't turn on your light, on average, the city is going to have the city or the region is going to have a load curve that looks pretty consistent from day to day. And then the peak loads depend on weather forecasting for understanding like how much electricity are we going to need for air conditioning, for example. In every system, we need to build more capacity to provide electricity than we think we're going to use on the average day to put some safety in the system. And so all systems are built with a higher total capacity than we think we're ever going to need. And that's to ensure that maybe what if one power plant goes down, for repairs or something like that, right? We need to have more capacity in the system than we need. And this actually is a really important thing to remember when we start to talk about renewables, because renewables actually, at the moment, mean we need to increase the amount we overbuild to ensure reliability. And that we'll talk about that in a future video. So the concepts I want you to take away from this slide are that there's base load that can be sort of always on, but always needed. And then we have to deal with the fluctuations of demand by having other kinds of power plants and more power plants to turn on when we need them to turn on. So how does this work in practice? Your independent system operator receives what are called offer curves from power producers. So if natural gas power plant says, okay, I can provide this much power over the next 24 hours. And this coal-fired power plant says, okay, I can provide this much power over the next 24 hours. So the ISO receives all these offer curves, and each power plant says, I will charge you this much for the electricity. The ISO also figures out what they think the demand is going to be, and they get commitments from the generator to provide enough supply for what they think the demand will be. And that is called the day-ahead market. So there's a pricing on a daily basis, a day in advance. So on the left-hand side of this diagram, you have the offer curve. So each independent power plant is offering electricity into the ISO. On the right-hand side, you see all the different loads or all the different demand that the ISO thinks there's going to be. So they forecast, okay, each one of these areas is going to require a certain amount of electricity, and so the load curves are shown in blue on the right. And then they do a whole bunch of fancy math to figure out the optimal solution for purchasing the electricity at the cheapest price, but making sure the electricity is available for all of those forecasted demands. And then the generator commits to pricing, and that power is purchased for the next day. But of course, we're not 100% sure what the demand will be the next day. We're pretty sure, but not 100% sure, because maybe it gets a little hotter than we thought it was going to get, and people use air conditioning more, or maybe it's cooler and they don't use as much. And so there are a series of post-market operations that go down to the sub-second level. Many of these are automated, and there are a series of less than day-ahead markets in play. I'm just going to talk very briefly about this one. This is the frequency modulation. You'll hear about this particularly when we talk about grid storage and batteries, which is why I bring it up now. And this is an automated market that essentially measures whether supply is higher than demand by looking at the frequency of electricity. So I mentioned before, when you turn on your vacuum cleaner, you might see a little dip in your lights for a second. And what's actually happening there is that demand is outpacing supply. And so the frequency of electricity, or the voltage of the electricity, is dropping just a little bit, or the power delivered is dropping just a little bit. And there's an automatic computerized system that then detects that and increases the amount of power being delivered. And that's not a human doing that. That's all automated, and it's tied to the frequency of the electricity. And that's a way of balancing supply and demand and making sure voltage stays constant, which is the goal. So that's the job of the independent system operator. They're supposed to run the market. They take the bids in from the generators. They anticipate demand. And they build an optimal purchasing agreement from all these different generators to all these different consumers, and run that market. There's another piece in the grid, another system in the grid, and that is the utility. The utility's job is to basically take the power that is coming through these high voltage transmission networks and distribute it to the end consumer, so an office building or a home. They buy this power on the wholesale market and sell it to the consumers, and they design retail rates, so you get your bill from them. They are the ones who manage the distribution network sort of on the consumer end. So if a power line goes down outside your house, they're the ones who come and fix it. And so the utility is really the interface between the independent system operator and you at home. There's one more intervener, at least in the United States, between the utility and the consumer, and that is public utilities commissions. In the U.S., at least, the utilities have essentially monopolies on the delivery of power. There's only one transmission line. There is a public utilities commission that usually has to approve what they're charging you for electricity. They have to both allow the utility to fulfill a revenue requirement and achieve a rate of return on their power sale, but they also need to ensure economic affordability to the consumer. And one of the ways they do that is they offer fixed rates. So if the wholesale market, day-ahead market, is fluctuating in rate, the utility can't charge a fluctuating rate as well. And so the Public Utilities Commission set a fixed rate for consumers. In some parts of the country, those rates vary with time of day. In other places, like where I live, they're set the same rate in the morning, afternoon, and evening. That protects the consumer from volatility in prices, but it also stops the consumer from responding to price signals. So for example, if there's a huge spike in electricity demand, I at home don't see a change in my price for electricity, so I don't have an incentive to conserve electricity. In places where rates are tied to demand, or at least tied to time of day, then you can respond to a rate increase by reducing your consumption. And that would be one way to modulate demand. So there are parts of the world that are really moving towards more flexible pricing during the day, at least, over the daily cycle, in order to allow consumers to respond to demand. So the 20th century grid is, as I've said, the most complex machine ever built. And it's really, again, utterly remarkable when you stop to think about it. how well it works. It's very rare for us to have blackouts. Sometimes storms knock things down, but the power is restored relatively quickly, at least in the past that has been the case. And so the 20th century grid is an amazing achievement, and the good part of it is that it has operated robustly and reliably for almost a century, and it provides electricity to almost everybody in the United States. The bad is that this grid is built around fossil fuel combustion to produce that electricity, and it produces the most carbon dioxide of any sector. In the US, actually, that's not true, but globally it's true. In the US, transportation is a bigger emitter, but globally, electricity is the biggest single source of carbon dioxide emissions. And sort of the ugly of the electricity grid is that this very, very complicated network is failing under climate change-related events. So we're having changes in storm frequency, changes in fire frequency related to climate change, and those things are challenging the 20th century grid. So at the same time as we've built this remarkable machine to deliver power to electric power to everybody in the country, and again, over most of the world, although with the caveat that there are many people living without adequate access to electricity, we've built this amazing machine. It's being challenged by climate change, and in fact, it is the cause of climate change, or it is a major cause of climate change. So how do we transform it? And how do we transform it in a way that provides people the consistent, reliable power to which we are all accustomed and upon which we all depend, but at the same time reduces the emissions to zero eventually, and hopefully fairly quickly, from this major source of climate change of greenhouse gases? So we've talked a little bit now about the electricity grid architecture. The rest of the videos about renewable electricity and the challenges that that transition will pose to the 21st century grid, as well as storage and flexibility of demand and electric vehicles, will be given again by my colleague Ram Rajagopal at Stanford, one of the world's experts in the electricity grid and how it works, but also how it can be transformed to a consistent, reliable source of electricity that no longer emits greenhouse gases. So I hope you enjoy those videos, and I look forward to our conversation.